In this video, we're going to learn about some theories of bonding and structure and how they apply to molecules and get us started into thinking about how these theories of bonding are used to understand organic molecules. All right, so it bears starting with a little bit of background here, which is just to remember that molecules form, maybe more specifically bonds form, because overall it is a stabilizing thing to mix atomic orbitals to create new orbitals, and then it is also stabilizing to pair up electrons. So there's two different things going on. The first is again that you mix orbitals to create lower energy orbitals that electrons can be in, and then the second thing is you're taking unpaired electrons, pairing them up, and then putting them into those more stabilized orbitals. As a consequence of the fact that mixing these orbitals makes things stable, atoms will come together to make molecules, and these molecules seem to put these atoms into certain geometries. And so based on that, we've kind of come up with a theory around how to predict these geometries. And you've learned this as VSEPR theory, valence shell electron pair repulsion theory. And the idea there is that there's these electron domains around an atom, and they kind of repel each other maximally to place these electron domains as far away apart from each other as possible. And then that leads to specific geometries. So for example, this nitrogen atom in N2 has two electron domains around it, so you get this linear arrangement on the nitrogen atom. BH3 here is a trigonal planar geometry. You have things like water, which is bent. You have ammonia, which is got four electron domains, but unevenly, so that's trigonal pyramidal geometry. And then finally, carbon tends to have a tetrahedral geometry. And so these are the most important geometries we want to be able to keep in mind for organic chemistry. And so with these observations of what molecules look like that they have a certain geometry and structure, historically there was a need to come up with theories to explain why these geometries and structures were the ones that existed. Right? So VSEPR theory is not really enough to explain the why of it all. And so from the historical development of theory, two ideas came to rise that are now very commonly used by organic chemists. And they both have their pros and cons, and they both do a decent job of explaining what's going on. So these two theories are first valence bond theory, or VBT, and secondly molecular orbital theory, or MO theory. So the idea with valence bond theory is that we're taking two singly occupied orbitals, and that we're looking at only valence orbitals, and that these two singly occupied orbitals are paired up and mixed to make a bond. So two unpaired electrons paired together, and then also at the same time those two orbitals that those electrons are in are mixed to make a new bond orbital. An additional piece we have to do with valence bond theory is to hybridize our atoms. So we use hybridization in order to get the orbitals to match what VSEPR would predict for the geometry. In contrast, molecular orbital theory mixes all the atomic orbitals of an atom, or all the atoms together, to create bonding and anti-bonding molecular orbitals, and that these kind of overall define the molecule. So again, the big contrast is in valence bond theory, we define one bond at a time. With molecular orbital theory, we're defining the entire molecule all at once. So why don't we look at a comparison of how these two theories treat the molecule of methane, CH4. So if we were looking at the molecule of CH4 here, for valence bond theory, what we would say is that we would treat, again, each bond as its own independent entity. And so here we would say that each bond is made up of a hydrogen 1s orbital overlapping and mixing with a carbon sp3 orbital, and that each of these orbitals would have one electron in them, allowing them to pair up orbitals to overlap. And so practically what this looks like is we have to be able to think of the atom initially starting off as kind of a regular carbon atom with all of these kind of 2s orbitals and then all the 2p orbitals. Notice that these 2p orbitals are orthogonal to each other, which does not match tetrahedral geometry. And so because of that, hybridization is what we do. So we mix the 2s orbitals with the three 2p orbitals to get four sp3 orbitals. I'm showing one sp3 orbital here for now, And of course we have to recognize that if we do this right, the math makes it so that you get 4 of these sp3 orbitals kind of organized exactly in the right geometry for a tetrahedral arrangement like you would expect for methane. Now once that carbon atom is hybridized, we can go and define our CH bond as the overlap of one sp3 orbital from carbon and a 1s orbital from a hydrogen atom. Of course, you'd have to do this 4 times to get to the methane molecule. Another important way to think about all of this theory is to be able to do not just the visual of it, but also the energy level diagram version. And so we'll do that again right here. And so if we're thinking about energy level diagram, what we're doing is we're taking that 2s orbital of carbon, taking the 3 2p orbitals of carbon. We're mixing all of those together to do our hybridization to get to a carbon where there's 4 degenerate sp3 orbitals. In case you haven't seen the notation like this before, when people draw energy levels right on top of each other, they're trying to save space horizontally and indicate that those are degenerate. So they're not different in energy. So once the carbon is hybridized, we again go to make our CH bonds one at a time. And so what we're doing then is we're taking a carbon sp3 at a certain energy level, a hydrogen 1s orbital at a certain energy level. Turns out it's a little bit lower than the sp3 level. They mix together to get to a lower in energy kind of bond orbital. And so if I go in and fill in my electrons, then it would look like this, where this diagram is trying to explain one CH bond in methane. And so I could kind of draw 4 lines on the left here and 4 lines on the right here, mix them all together to get 4 lines in the middle to indicate that I've made 4 bonds, 4 CH bonds. Okay, now let's look at molecular orbital theory's treatment of CH4. So again, the idea is that we're just mixing all of the atomic orbitals together. We're not dealing with one bond between 2 atoms. We're just dealing with all 5 atoms and all of its electrons all at once. And so we're mixing all of these atomic orbitals through a process called linear combination of atomic orbitals. This is actually no different from what's done on the left here to do hybridization, for example. It's always kind of taking 2 equations, which are orbitals, mixing them together. The difference is on the right here with molecular orbital theory, we're mixing a lot of orbitals together. Another comment I've made here is that they need to be of similar energy, and so this is generally going to be the case, that only atomic orbitals of similar energies will mix. In general, that means we're just looking at the valence level of orbitals, and those are the ones that we'll be mixing. So as an example of this, if we look at CH4, then what we're really doing is we're taking a 2s, 3 2p, 4 H1S's here, mixing them all together. And it's a little bit hard to visualize all this, so I just have an image to pull up here. Turns out that this is what you get for the various orbitals. If I turn that into an energy level diagram, then it looks like so. And so what you'll see is there's a lot going on here. On the left, I have the carbon atom's atomic orbitals. On the right, I have the hydrogen's atomic orbitals, and I've just put all 4 of them here. In the middle, I have the entire mixture that comes out of this. So if you put in 4 plus 4 is 8 total atomic orbitals, you need to create 8 total molecular orbitals. If I go and fill in my electrons, then what I'm doing is this. Saying I've created all these orbitals and I'll fill in all these electrons, so 8 total. That gets me to energy level diagram that looks like that. You might be wondering, well, how do you get to the middle? What is going on here? Turns out it's a fairly complicated process, of course, but we can make some connections that, for example, the carbon 2s and the H1s have some level of interaction right here. And with molecular orbital theory, a big concept is that every time you make an orbital that is more stable in energy than the 2 orbitals it's mixed from, you create an antibonding orbital that is less stable. And so that is this one up here. And so what you might note is that this molecular orbital is created from mixing this carbon 2s and just really essentially one of these H1s's. So that's kind of weird, a little bit different from valence bond theory. The kind of 3 degenerate levels in the middle then are essentially from the remainder of those H1s's. and then you get the kind of anti-bonding versions there. And so overall, CH4 exists as a molecule, according to MO theory, because we can mix all those atomic orbitals, we can create bonding molecular orbitals, and we fill more bonding molecular orbitals than antibonding ones. In this case, we don't fill any antibonding ones. When it comes to viewing these molecular orbitals or these kind of valence bond theory orbitals, I think it's helpful just to be able to see a little bit of what this actually looks like. So I'm going to pull up the 3D models for these. So I'm going to first pull up the valence bond theory version of methane. And so if you're looking at this, you can kind of see on the left here, this is a hydrogen atom. And so what you're looking at here is kind of the 1s of hydrogen mixed in with the sp3 of the central carbon here, and this is one of our valence bonds. And so I can kind of go through and turn on the other 4 of those bonds, and so that's what you're kind of seeing. And this is the picture that we're building if we're using valence bond theory to understand methane. Okay, now let me go through and pull it up for molecular orbital theory. Okay, so here is the molecular orbital theory version for methane. I'll start with the lowest molecular orbital here. You'll see right away that the color that I'm showing on the screen is different from the one that I did in the in my little drawing out here, right? Turns out these colors are just artificial colors. They're supposed to indicate whether something is positive or negative, or like what phase it's in. So this is just an arbitrary coloring. And so what you're kind of looking at here is the lowest energy molecular orbital that encompasses all of the atoms. If I go up to one of the higher ones, what you see is that the molecular orbital doesn't just define one CH bond. Right? It doesn't look like that at all. There's kind of this weird pattern to it, and what you're looking at is actually essentially the p orbital of a carbon mixed with one of the H1s here, another H1s here. And so that happens multiple times to get us 3 degenerate molecular orbitals like so. And so my point in showing you these is not to expect that right away you're able to construct these 3D images in your mind. That's not at all the point. The point is to tell you that there are 2 theories that we're going to use in this class, and they actually come up with pretty different explanations for bonding in molecules, and we just have to be aware that there are different explanations behind these 2 theories. And so naturally you're going to wonder, well, when should I use valence bond theory and when should I use molecular orbital theory? So they definitely have their pros and cons. Valence bond theory is a little bit less accurate, but it's much easier to do in our heads because we're building everything from VSEPR and we're only dealing with 2 atoms mixing orbitals at a time. Molecular orbital theory is a little bit more accurate, but it's basically impossible for a human to do because of the math involved when you try to mix 20 or 30 or 40 atomic orbitals together. And so the balance of this is that people will tend to use valence bond theory to talk about structure. And what I mean is that if I look at a molecule like this one right here, what I will say is I'll look at this carbon and say it's an sp2 carbon. That causes me to think about trigonal planar, and it causes me to realize that in an sp2 carbon there is a p orbital that hasn't been hybridized with the others, so that's part of this pi bond here. If I look at this atom out here, it's an sp3 carbon because there's 2 hydrogens coming off, and so that causes me to think, well, that should be a tetrahedral geometry. And then finally down here, it's an sp carbon. I make some connection to it being linear. And so that's kind of big place that people will start with valence bond theory. In contrast, molecular orbital theory is really good for thinking about kind of the actual energy levels of a molecule. And when we get to reactions, it'll be very useful for thinking about the reactivity of a molecule. And so I want to give you a quick example of what that looks like here. So a common question we'll have is, well, which bond is more reactive in a given situation or in a given molecule? And so what molecular orbital theory allows us to do is to kind of look at, let's say, a carbon-carbon double bond, and we'll look at just the pi bond, which comes from mixing 2p orbitals here, and compare that to a carbon-nitrogen double bond, again coming from 2p orbitals overlapping. And so keeping in mind that nitrogen is more electronegative, that causes its atomic orbital to be lower in energy than the carbon atomic orbital. And if this is pulled down in energy, relatively speaking, that causes the molecular orbital to be pulled down, relatively speaking, in energy. And so what that means is that if we're thinking about the bonding orbital right here versus the bonding orbital right here, molecular orbital theory will tell us that the one on the right is lower in energy. That means it's more stable. That means it's less reactive. And then that tells us that a carbon-carbon double bonds pair of electrons should be more reactive. Conversely, if we're thinking about electrons trying to enter into an empty orbital, we would expect the electrons to prefer to enter into this molecular orbital over that one, because this one is lower in energy. Now that's an idea, again, that we'll come back to in later videos, but I just wanted to bring it up now to show you the importance of molecular orbital theory. Another way that you can kind of divide up the usage of valence bond theory and molecular orbital theory is to think about the different types of bonds in the molecule. And so valence bond theory tends to be most useful for thinking about sigma bonds. And so to remind us what those are, sigma bonds are when you overlap two atomic orbitals in a way that makes kind of a cylindrical geometry. So if I look down this axis right here, I'm going to see a cylinder, and that's kind of considered a sigma geometry. That relates back to this original point of structure in geometry, where the sigma bonds make up the backbone of your molecule, and so valence bond theory is what we use to figure out what that looks like. And then on the other hand, molecular orbital theory tends to be very useful for pi bonds. We'll talk more about this in the delocalization video. But just to review what a pi bond is, just in case, pi bond is when you get kind of side-by-side overlap of atomic orbitals in a way that creates a planar node halfway down here, so that the top half is a mirror image of the bottom half. So just to summarize all of this, there are two very useful and complementary theories for explaining molecules. We have valence bond theory and molecular orbital theory. Both of these are trying to explain the actual geometries and structures and properties of molecules. And they definitely both have their pros and cons, and we want to be able to use and understand how both of them work. Not that we're going to go sit there and generate a bunch of very complicated diagrams, but rather that we're able to just talk about them very quickly to analyze molecules and discuss what they look like and what they do.